All right, so we are talking about categorical data. And today we are going to be able to answer the question of, is the data that we see for categories what we expect? Or is it going to be something different? What we will be doing is called a chi-square goodness of fit test. Now, chi-square is just a test that tests categorical data, okay? This is like an x chi-squared, okay? And right now we are going to test whether, and we're going to change what this question is, it's Skittles. We're going to say that M&Ms, they say that they have 6 colors, and that the mix of colors of M&Ms is equally distributed. Now, like you might have, a couple extra of this and a couple less of that, but the question is overall, if we look at everybody's data, will we find that there's the same amount of yellows, reds, blues, oranges, greens, browns? That's pretty impressive. Okay? Now, here's the key to this lesson. The key is we want expected values, okay? We are going to test, what is this, amounts of categorical data? I have this somewhere. Counts. Test counts of categorical data, just like amounts. The test is going to measure how far the observed counts deviate from the expected values. Okay, observed and expected. Now, expected is the most important part. We have to be able to calculate the expected total. Okay, so let's say I have 100 M&Ms. And I want to figure out how many blues we should have based on what they claim. They claim that all of the M&Ms should be equally distributed. Okay. Well, how can I find the expected amount of blues if I have 100 M&Ms?
How many colors?
Right, there are 6 colors, so let's change this from 5 flavors to 6 colors. So I have 100, I'll divide it by 6, or I'll take a total, so I'm going to multiply the total sample size by each category percentage. Well, if they're all the same percentages, I'm going to multiply the total by 1/6, which is a percentage, and I get 16.6667. Okay, now that's going to be the same for reds, for yellows. I'm going to expect 16.67, right? And that's just the total times a percentage. This is important, this type of calculation, finding expected. Okay, now we will be able to test an hypothesis. We'll be able to find a p-value. So the hypothesis is always going to be the true portions for all categories are the ones that are hypothesized, or the same as the hypothesized. The alternative hypothesis is that the true portions are different than the hypothesized. Okay? So let's do the test. Everybody, let's go down here and let's change it from Skittles to M&Ms. Everybody has a handful of M&Ms. We should have all counted the color that we have, and we're not going to put it on the board. I'm just going to go around and ask. We're going to then add up each color that we have, and we will go from there. Our hypothesis, we are going to try to figure out whether M&M's claim is true. Do the proportions of M&Ms, are they all equal in terms of colors? So the hypothesis is always going to be for this categorical data, are the proportions of M&Ms all 1/6 of the total. Okay, that's M&M's claim. The alternative hypothesis are all the proportions, maybe not are, but the proportions. The proportion of M&Ms are all 1/6 the total. The alternative is the proportions are different. All right. Let's go around and figure out what everybody's amounts are. And we find a total. The total is extremely important to have. So let's go around. Mr. Champagne, how many M&Ms do you have? Miss Burke? Unlucky. Lucky. Unlucky. Lucky. Lucky. Unlucky. Oh my goodness, super lucky. 17. Mr. Funk, how many do you have? Super lucky. In the middle. Lucky. It's May. Lucky. Mr. 16, lucky. Unlucky. Super lucky. 16, in the middle. Put your phone away. Mr. Rios. In the middle. In the middle. In the middle. Lucky. Unlucky. Okay, we have a total of 324 M&Ms in the house. Well, this is important. Once you have the total amount, you can find the expected amounts of M&Ms for each color, right? So if I have 324 M&Ms, how many blues can I expect? We're going to go ahead and assume you have 17. It's going to be okay.
Average.
What is the expected amount of blues? $54 on the dot, right? I just got 54 on the dot. Ah. Good. Well, how many reds should I get? 54. How many greens? Are greens a color? Yep, greens, 54. Browns, 54. Yellows, 54. Did I miss one? Yes. Orange, 54. Okay, this is very important. How do we find these expected amounts? We took our total times our percentage. In this case, the percentage is each 1/6. So the percentage is like a ratio. But sometimes I'll give you just a percentage, like we expect out of the 5 colors, it's 10% this, 20% this, 30% this, and you have to multiply the specific percentages by the totals to get your expected amounts, okay? Well, let's find the actual amounts. Blues, hold up your fingers for blues. How many blues do you have? 2, 3, 2, 1, 2, 2, 1, 5, 3, 6, 4, 1, 2, 4, 3, 5, 2, 2, 4, 3, 5. 62 blues. Now, we compare the blues to the actual. Is it far off? Maybe. Maybe not. I'm not sure. It's all going to be how close are they? And what we will end up finding is the probability of getting these actuals if these expected amounts are true and if this null hypothesis is true. Let's go to reds. How many reds do we have? 3, 2, 5, 2, 4, 2, 1, 1. Reds. Put your phone away. That way I don't have to freaking come over here and tell you to put your phone away. 2, 1, 1, 1. 0, 4, 3, 2, 1, 2. 41 reds. Okay, looks like it's a little below our expected. How many greens do we have? 3, 3, 1, 1, 2, 2. 6, 4, 4. 0. 3 or 0? 3. 2, 2, 0, 0, 2, 4, 3, 4, 0, 3. 49. Those are greens that we just did? Okay. Blues. Browns. Sorry, browns. 2, 1, 2, 4, 2, 2, 1, 2, 3, 1, 3, 3, 3, 2. I think I said that. 2, 1, 1, 4, 2. 41 browns. Yellows. 1, 0, 4, 4, 2, 3, 3, 4, 5, 1. Goodness gracious, Mr. Funk.
I'm not even on my phone.
I know, so what's going on now?
Because I was trying to get all these numbers down, and then I was like... Okay.
Literally, we write a number. We've written a number every 20 seconds. It should not take you very long to write down your numbers. You must be on your phone or something. 6 yellows, Mr. Meyer. That's impressive. 3, 0, 2, 1, 1, 1. 48. Well, let's... Orange. 4, 5, 2, 2, 4, 4, 3, 2, 5, 3, 3, 6, 5, 4, 6, 4, 2, 5, 3, 6, 2. Oh my gosh. 80 oranges. This is out of control. All right, let's see if my counting was correct. 62 plus 41 plus 49 plus 41 plus 48 plus 80. 321. I'm off by 3. Let's call it 42 reds, 42 browns, 49 yellows. Okay? Here we go. We get to find a p-value. We get to find if this is true, how likely it is for this to occur. Okay? If this is true, how likely it is for this to occur. That's what a p-value is. Remember, p-values are not just random numbers that we compare to significance level. It's a probability that the observed will occur if the claim is true. If the p-value is smaller than the significance level, we say that it is so unlikely to occur that the null hypothesis should be rejected and that the proportion should be different. So this is reject the null hypothesis. The categories are different and stated. And we know if we have a large probability, then this is likely to occur if the proportions stated are true. The categories, don't say are true, or just say the categories of the claim could be true. Say your conclusion in context of the situation. Don't just say reject or do not reject. Tell me what you're rejecting and tell me why and what it means. Okay? Question, Ms. Rios. Different than stated. Sorry for my poor penmanship. Okay, now, this is how we're going to find it. You're going to go to Stat. You're going to go to Edit. You're going to put Observed in L1. You're going to put Actuals in L2. Observed in L1, you're going to put expecteds in L2. Okay? So Stat, Edit. Whoa. Up, clear, enter, 62. Yes. Yes. is a very good question. Whoops. Mr. Englander said, if these weren't all 54, would we have to match up these with these? Yes, definitely. That's the whole key to the chi-square test. Okay, 62, 42, 49, 42, 49, and 80. Over here, 54s for section 1. 1, 2, 3, 4, 5, 6. Okay, now we will go to stat test. The chi-squared GOF test. It's under B. Some calculators actually don't have it. Stat test, chi-square GOF test. If you don't see chi-square GOF test, you're going to need to use another calculator. Okay, we got that? What do I say to what? I did not say that yet. The degrees of freedom is going to be your amount of categories minus 1. Yes. Degrees of freedom is categories minus 1. So we have 6 categories minus 1. That's going to be 5. I'm actually going to have to check that. I feel like it might be our sample size minus 1. Let's do it both. We calculate it. And this is the probability of our observed occurring if the expected is true. This is a low probability, which means what's probably true? That they're not equal to 54, that they're not going to be 1/6. Okay, so that's the important thing. There is a chi-squared test statistic. Don't worry about putting that down. It means nothing to you. Nope, don't put the 19 down because you don't know what it means, but you do know what a p-value means. You did know what z-values were and what t-values were, distance away from the mean on a normal distribution. So that's why you put those down, but for this one, we don't know what the chi-square means. But we do know the p-value is very small. It's definitely less than 0.05, which means that the null hypothesis is probably false. I'm going to reject the null hypothesis. Proportions are probably different. I'll just say proportions of M&M's colors are not the same. It looks like orange and blue are the popular colors to M&M or to people. And I believe M&M's make sure that they put more blues and oranges than every other color.
Maybe it might be cheaper.
Maybe the colors are cheaper. Who knows? I don't know. You can now eat them. Okay, so that is how we can see if the data we observe is going to be close enough to our accurate to say our proportions are true. Flip to the back and go to number 2, this Mendelian theory. It's all about biology. Anybody in AP biology? Did you do a chi-square analysis? Cool. So you're pros. Well, this should be right up your alley, this Mendelian theory of inheritance. We take 2 peas and we breed them and we see which traits that they pass on to their baby peas. Okay? Cross-pollinate, I believe, is what like the biologists say instead of like breeding. Okay? But we're taking 2 peas and we're making babies, right? Here we go. We believe that they will occur in a ratio of 9-3-3-1. What? That we'll have round in yellow, wrinkled in yellow, round in green, wrinkled in green in a 9-3-3-1 representation. The respective percentages are going to be 56.25 for round in yellow, 18.75 for wrinkled in yellow, 18.75 for round in green, 6.25 for wrinkled and green. Now, those are your expected percentages. The observed frequencies are 315, 101, 108, and 32. This is what we put in our L1 for our observed. Okay, so go ahead and L1, put those for your observed. The green, right? Observed counts. No. I'm just putting the observed in right now into L1. We have not talked about our expected values yet. So don't put in the percentages into L2 because we haven't talked about that yet. I'm just saying you have observed, go ahead and put them in. Now, if I had this many P's and this was true, how could I find my expected values to go into L2? Thank you, Miss Adams. Perfect. We got to figure out our total. We got to figure out how many total P's we have. And then once we found our total P's, we'll multiply them by the percentages. Just like in this problem, we found the total amount of M&Ms and we multiplied them by our percentages, okay? That's how you find your expected values. You got your total times your percentages. What is the total amount of P's? 556, okay? Go ahead and find the expected amount of round and yellow P's, wrinkled and yellow P's, round and green P's, wrinkled and green P's. Compare your answers with a neighbor. Yes, we'd have 3 degrees of freedom. 312.75. Questions? Yes?
Okay, so am I taking the 315 and multiplying by that?
Nope. You're taking your total amount of P's that you have.
Oh, by each of them. Okay.
So you add them all together, and you know we have 556 P's, and then we multiply 556 by each of the percentages. You could do it in your table. It's actually not that bad. 556 times 0.1875. $104.25. What would be the next one for round and green? Right, it'd be the same thing because it's the same percentage. What do we get for wrinkled and green? 34 on the dot, 0.75. Total by your percents. I expect 56.25% of my P's to be round and yellow. Total times the percent gives you the total of that. Okay, so we have 34.75 is the last one. Now, before we go even any further, let's write down our null and our alternative hypothesis. Our null hypothesis is that the Mendelian proportions are correct. Alternative is that the Mendelian proportions are not. Not correct, or they're different than stated. Okay? Now, if we get a large p-value, then we can say Mendelian could be true. If we get a small p-value, we say Mendelian is a fool. Let's find out. Stat test. Now, if you want to go to alpha D, instead of going all the way down to D, you go alpha D. And it takes you right to this chi-squared GOF. What is going on with your pen? It's pretty impressive. Right by Miss Nebergitch, bottom left. Thank you. Thank you. Okay, L1, L2, degrees of freedom is now 3. We have 4 categories, minus 1 is 3. Calculate. We get a p-value of 0.925. Oh my goodness. What does that mean? Very likely to occur, extremely likely to occur. So we say Mendelian cannot be rejected. Mendelian's proportions cannot be rejected. Mendelian might be right.
Alpha D.
Stat test, alpha D. Okay. Let's go.
What do we put in the two?
What?
Okay, so but on the list 1 and the list 2s,
Yep.
the observed is the actual indication.
Yep.
And the 4 multiplied by the proportion.
Yep. Okay. Let's all do number 1 by ourselves and then check with a neighbor. Question. Yeah. Go. Go. Number 1. Do it. Do it. You have 15 minutes. Oh, at 11:15? That's fine. Do number 1.
So effect is only right because I got an error message saying domain.
Yes. It looks like you did.
So I didn't know what it is.
Let's see. Stats. Test. Alpha D.
Yeah. Page 3, calculate, and you get the error message. It worked the first time, it's just not working this time.
L1, L2. L1, L2. What? No, you share. Yeah. Right. Perfect. The proportion for each class should be this. Yes. Right. It's because you didn't enter in the correct, you entered in the percentages. We shouldn't enter in the percentages. We enter in the observed, and then we enter in the expected. So the observed is 101, 108, 32. That was just so far away. Stat test alpha D. There. For the last one? No, it's not. Wait. Yeah, this one. 32. It shouldn't be 347.5. This is 556 times 0.0625. You should get 34.75. It should be 34.75.
Oh,
Yes, number of students is the observed. Okay, so now run it. And you get 0.92 as your p-value. Categories -1 is degrees of freedom. All right, let me come around and see these p-values. Looks good. Now, don't just say reject or do not reject. Tell me what it means if you do reject in context of the problem. My goodness. Yep.
Oh, it is?
1/7 is the percentage, but you have to multiply that percentage by the total amount of students here to find if we had this many students,
Okay.
how many would end up in each class.
Okay.
well, that's what no two.
The expected counts. If I have this many total students and they were spread evenly, that's the expected amount. Good. Good. Question? You're not sure what to do with the expected amounts? I have this many students and they were placed equally amongst all 7 classes. That would be the expected amount. So there's 7 classes, take this divided by 7. That's going to be each of those. Good. 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 All right. Now, stat test. D. Degrees of freedom would be 6. N minus 1. So let's change that to 6. Calculate. And you get 0.04. All right. So, there is a total of 119 students that were placed into 7 classes. The question is, the null hypothesis is, the proportions are in each class are equal. that means the students are not selective. They're just randomly assigning themselves into 1 to 7 periods. The alternative hypothesis is that the students are selective, which means some classes are more popular than others based on time, professor, or whatever. Time will be your number one importance next year. Don't have classes at 8 o'clock in the morning. The expected counts will be your total times. If they were evenly distributed, the percentage of each of these would be 1/7, giving us 17 all across the board. That's our L2. You get a p-value once you run test chi-square GOF of 0.04, which is just less than 0.05. So I will say, reject the null hypothesis. It appears students are selective. In their class decisions. Okay. All right, here's your homework. It's a lot of multiple choice. Why not?
I'm all right with that.
Go ahead and make sure your calculators are up. I should have 9. I should have 10, but right now I have 9. We're up to 9. I know. Yeah, where were you guys? We were pumped when we heard that you got 9.
I remember 8. 8 was a big deal.
8 was a big deal.
Okay, question.
6 and 7 were big deals. 9 is a big deal. We were 1 away, guys.
You were down to 5?
We're down to 5. Sure.